Okay. Hello everyone. Welcome to Implants Paper Club. Today, my name is Vahan. I'm presenting a paper from collaboration from Stanford and Columbia Universities. Uh, this is from my CLR's special mention papers, uh, and it's about testing or provably testing benchmark contamination from LLMs. And this is very important because every time there is a new, better, bigger LLM, uh, they always beat the benchmarks, right? Uh, because benchmarks are openly available, but usually, even if the model is open, the training the data is not published, which means we don't know if the model has been trained on the benchmark, right? Uh, Very often with published papers, there is a report on evaluation on contaminations. However, it's not always the case, especially for proprietary models. But also we want a third party evaluating, right? So this paper is one of those efforts, and this is the first one that has provable guarantees, statistically provable guarantees. Okay, so Uh, the paper is called Proving Test Set Contamination in Black Box Language Models. So test set is the benchmark. Contamination, we spoke about this. Black box basically means we don't have access to the weights, or even if you do, we don't know what training data it used. And proving because they do give proofs about guarantees. Okay? We are going to develop statistical tests with null and alternative hypotheses and base the theory on that. And then there will be lots of experiments evaluating the test. Okay? Um, I gave the abstract. I should just add that the idea here is based on the assumption that usually those benchmarks are invariant in terms of the order of questions. Not all of them, as we will see at the end, but almost all of them don't depend on the order of examples, right? So the hypothesis here is that we can shuffle the order and see if the probability or log probability changes of giving the right answer, right? Which means no, not the right answer. The log probability of the sequence changes. Which means if if one of the shuffled samples has higher probability than expected, then probably this was observed during training, right? That's the main idea here. But there are a few things we have to sort to make this work. We spoke about the introduction. They mentioned a few. They mentioned the benchmarks. There are a few benchmarks covered here. And an example here, let's look at this example first. So this is one of the test sets, bool Q, which is a true or false question answering the data set. You can see various questions. They are kind of random, right? They don't depend on each other. And you have the canonical order, but you can also shuffle the order, right? You can see this is the last two are shuffled. And then the test will say, is any of those more likely than the rest? If that's the case, then the null hypothesis can be rejected. Okay? So let's scroll a bit lower. They call this hypothesis exchangeability. So we will refer to that in the theory. Exchangeability means we can shuffle the order and the order of test set, and then it doesn't matter in terms of the model's output. Okay, the probabilities from the model's output don't change, which means all we need to run this test is the log probabilities of from the model from any given output. So we only do forward passes and get the log probabilities. We don't just get the most likely cases, but we need the log probabilities, okay, which is usually what you get from all models. So we can use this approach to test any model. We don't need access to training data or anything else. That's very important. To summarize results, what they observe is that uh, their test works well if the contaminated data is repeated 10 or more times, sometimes even as low as 2-4 times. But if it appears only once, the test doesn't work. It can't detect those. But that's okay, because normally if the data is seen only once during training, it doesn't usually have much impact on the model's performance anyway. Okay. The main contributions, as I said, they demonstrate the use of this exchangeability assumption for using only log probability queries to assess if the training set was contaminated. Okay, it's good. They construct an efficient and powerful hypothesis test. We'll talk about the sharded approach, which makes the test efficient. Otherwise, it's not actually efficient. The powerful means if you don't do the sharding approach, the p-values you get can never be low, which is a bit of a problem, right? If your p-values can't be low, your test doesn't make sense. But they solved that problem introducing sharding. We'll look at that later. Um, uh, they do empirical demonstrations for black box model detections, and actually they don't find anything massively wrong. There are a couple of models that are suspicious, but there is nothing spectacularly contaminated. Okay. I was hoping there would be like, oh, GPT-4 has been hugely contaminated, but that's not the case. They don't find anything like that here. Okay. Any comments here? Questions? Cool. Let's define the model, the problem mathematically. So we will have a null hypothesis, H0, and an alternative hypothesis, H1. The null hypothesis is that, well, theta is the language model, and X, well, no, so sorry, training process of language model. Theta is the language model. Data set X is the test set we want to evaluate. Now, null hypothesis is that theta is independent of X. Okay, that's a good thing. But then we will assess if we can reject the null hypothesis. In which case, there is a good chance that it's not a proof, but there is a good chance that the data set has been contaminated. Okay? That's how statistical tests work generally. And then we will also show that the false positives, falsely rejecting null hypothesis with probability at most alpha. So this alpha is important, right? We want to minimize this falsely rejecting null hypothesis, which is why we will convert this test into a t-test, actually, for which we have theoretical guarantees. Okay? T-test is a well-studied test, and that's why we convert it into t-test, so we can have theoretical guarantees. Cool. Right, we will look at these pies, which are the shuffles. These are permutations, and we will look at random permutations. And the first proposition, the main proposition here, is that yes, Peter, go ahead.
So this was a part of it that, so here we're talking about how, so this assumption here, or proposition one, the thing about it that I think doesn't fully make sense to me is that say that each individual example in the test set is in the training set, and it's they're loaded independently of each other. I could understand if you load the whole data set at once in order to train the model, but most likely you're loading independent examples. And if you're doing that and you're using standard procedure for training these models, you should be doing like, you should randomize the ordering of your training set, and then also batch it. So why would the ordering that why would they use the ordering in the training set that is like the ordering that you load the examples in? So that was something that I was like, well, this is assuming that there's, or at least I think it's assuming there's no randomization in terms of ordering the data set.
It's about training though. So this sequence first converts the data set into a long sequence, right? I think this is about inference.
No, but the assumption is that like it's memorized the ordering of the data set. But my like and so if it hasn't memorized the ordering of the data set, then these two log probabilities will be equal. But if it has, then most likely the left log probability will be larger than the right log probability.
Okay, so let's actually break this down. So there is one assumption here, right? Exchangeability. The other thing we use is independence, is the null hypothesis, that theta is independent of x, right? Independent means not for training. I think this is about inference. So I'm not sure if it matters how it was trained, unless exchangeability problem.
If you go, it's talking about how because the whole point is identifying whether the some data set X was in the pre-training data set.
Yes.
And the assumption is that those two should be equal if it hasn't seen the training set. Those two log probability should, if it hasn't seen the training set, I mean the test set in the training set, right? But if it has, it's saying they shouldn't be equal because the model will have memorized the ordering that it sees of the test set during pre-training.
And you are saying that because of batching, the ordering may have changed.
Well, just because we do like stochastic, you usually reorder the entire training set when at every epoch, and probably you should, as good practice, reorder it at the beginning of the like at the beginning of the first epoch as well.
I think that the test sample would basically be part of a single sample though, because for large language models, the way that they tend to train them, from what I know, is you get all of your data and it's just basically text, and you just have loads and loads, and you concatenate that all together. So you're not really training it as lots of individual samples. You're training it as one very, very, very long sample, and then you slice that up. And so I think the chances of a test, if it's a small number of tokens, staying in order is very, very high in that situation. So you're probably never going to get them where one line comes before the other line. You might get it where your batching process slices it in half, and then they'll end miles apart. They'll be miles apart in the training sample. But yeah, with training LLMs, it's basically just one super, super long input, and I think that solves this problem.
That makes sense. Okay, thanks.
Cool. Thanks, Andrew. There's a similar comment also in the chat. I think that makes sense. Cool. Let's continue. So there is this assumption based on that exchangeability assumption and null hypothesis, we can show that the log probability of having the X sequence and the permutation of X sequence should be equal. We spoke about this before, and we will build the rest of the theory on this. Okay. And then we also want, and then we say, in case that's not the case, this will become an inequality here, right? Because X will become more likely than a random permutation, much more likely actually. I think that's it. Okay, let's talk about the method, how we devise the statistical test. There are two tests here. The first one is that actually we put that inequality here, right? Get the expectation over the permutations, all permutations, and we calculate the probability of this condition being true. So there is one is basically saying this is 1 or 0. Okay. Yes, Peter.
Okay, here is another point of confusion for me. but it was just more like I'm keep looking at this and I'm not getting it. So if the probability is higher, is that the probability of the null hypothesis or the other hypothesis?
The alternative one. Okay, so normally you would say, so this will become a log, no, this is log probability. So this P would be the P value. So if it's very low, then you can't reject the null hypothesis. If P is small, then you cannot reject null hypothesis, which means the alternative is likely. So basically, if P is small, then you can assume that there is contamination.
Okay, so if we take P to be small, that means that the likelihood of the original ordering is
small, then is in expectation is more than all permutations.
So yeah, it would be that. But so for the test set, it would be the likelihood of the original ordering is greater than or equal to the permuted ordering.
So if this is true, then wait, did I mix it up again?
No, I think what you're saying is correct.
Correct, right? So if this is often true, so you get lots of ones, you would get that null hypothesis cannot be rejected. Yeah, and then P would be large, and you can't reject null hypothesis, which means there is no contamination.
Yeah.
Right.
Mm-hmm.
Okay. It's often very confusing about like rejecting null, not rejecting alternative, or whatever. But I'm trying to be careful with my language here to not say the wrong thing here.
Mm-hmm.
Obviously, we can't calculate the expectation over all permutations, so we approximate this. We do this plus once for stability reasons. These are standard things, so the expectation becomes a sum up to m of them. Okay. However, there is a problem here. So because this sum can't be negative, this means our p cannot be less than 1 over n plus 1, which means if we want p to get close to 0, we need very, very large samples here, 10 to like 11 range, which is not practical. Okay, which means this test is not very useful because it can, in practice, it can never give a small p. So what's the point, right? So we have to solve this problem. There is another problem here actually also, which is we spoke about this, but also the computations, right? The computational complexity for the runtime is m times size of the data set. Again, you have to make m large, this which means the computation gets very large here. Okay, so we don't like this. Instead, we have to come up with a better approach where we allow smaller p. We will see in the experiments also that this happens in practice also. So to come up with a smaller p, what they do is they create this sharding approach, okay? Which means we basically split, we shard, we split the data set. You go down here. So we have this. We partition the samples into n partitions, and then we have this R contiguous shards. Okay, we create R shards, okay, which are the shuffles. Okay, where each shard S contains at least k equals n over R examples. So we make sure that there are enough examples, so they are approximately equal, but not because of the division problems. It's not exactly equal, but plus minus 1 equal. Okay. So we create these shards, and now the test becomes not the expectation over the difference here, right? Because this is the expectation over the here. This is basically expectation over the difference between each sample. Here we do the mean only on the permutations, and then we can get the difference from the x log of x from the mean over permutations of log x pi. Okay? So we move the mean here. There's a comment here. Let me check. Side comment. Okay, everyone read the comment. There is a interesting thing here. Helpful for understanding p-values. All right, there is a guide for understanding p-values. Thank you, Dwayne. That's useful, actually. Normally, we want very small p-values, but often you would say if p is less than 5%, then we can reject the null hypothesis. That's the usual thing. But you want p-values to be very small. We will see the examples at the end. Okay. Now we have this S now, and then we approximate S as we take the average of SIs for all shards. So this SI is for the shard, right? And then we get the average, and then we use a zero mean. We test whether S has zero mean using the t-test. Okay. So we kind of convert our test into t-test, which is a classic test to check for zero mean. Okay. And then we can say that if checking for this zero mean with the t-test is equivalent with checking for our original null hypothesis. Okay. So we kind of broke the problem down into a more computationally efficient and well-studied problem. And the important thing is that now the p-value, so the p-value will actually become the log probability, right? Which means the p can be very small now. There is no lower bound anymore. The lower bound is really the floating point operations now, which is what we want. Okay. Now they define the algorithm. You take the inputs, the test samples, the target model, which is a trained model, number of shards. So this is actually not very large. They give the numbers. It's like 20, I think, or 50. We'll have some experiments to find the number of shards, and also number of permutations. Also not very large. And then we partition into shards. Partition the example into shards. The important thing is there is no overlap between shards. Because otherwise the theory wouldn't hold, because we can't assume independence between each sample, and then this t-test wouldn't work because we need IID samples here. Okay. There's a nice conversation going on. Okay, cool. There's a fun conversation about the p-values. We haven't had any statistical tests here before. I'm glad we are doing this. Cool. And then we calculate the log likelihood of the canonical order. So we have this order, right? These xi's are the order. We make it into sequence, get the log likelihood, and then we estimate the shuffled log likelihood with the mean, and then we calculate SI. Okay, and then for each SI, so these are for each shard. Then we get the average over all shards. And then we get the one-sided t-test if the expectation is larger than 0. And then we return the associated p-value from this test as the p-value we want. So this t-test will give us a p-value, which becomes the p-value for. Okay. There is theory here, which is actually based on the theory for the I highlighted important assumptions in the proof. We don't need to look at it, but it's actually fairly short. The important thing is that we assume that the distribution of the log p or log probabilities over the sequence of each shard is invariant to the permutation. That was the original assumption, which still holds. We use that the statistic SI must be zero mean. This is the test we use later. And we assume that each shard is independent, which is also fine because we can enforce that. And then basically we use the t-test, which checks if S is Gaussian with a zero mean. Okay. And then there is the t-test already has the asymptotic guarantees. Asymptotic because here we say that the probability that p is less than alpha minus alpha asymptotically goes to 0. Okay. Which is why now we have theory that says asymptotically the p-values get close to 0 for when the null hypothesis is rejected, which is a good property to have. Otherwise, you don't know if you are missing or if you are missing rejection points because p-value is large when it should be small, right? This guarantee is important. Okay. Yeah, I spoke for a bit. Any questions, comments here? This was a bit of theory. Well, hopefully, it's not too bad. Yeah. Okay. Let's look at some experiments. They do.
Maybe one question.
Yes. Yes, Arvid.
There's also this concept of the power of a test, right? That sort of says, given there is a difference, what's the likelihood that I find out that there is a difference? And it depends probably on the size of the difference typically. Now I don't know how this would translate to this problem, but by doing this, is it like a trade-off that one what's the trade-off here that one so sort of makes it less sensitive or more sensitive, right?
Yes, maybe I can find the experiments that actually talk about that. Let me see. No, where was it? There was a nice graph about that actually. I guess that no, these graphs are a bit different. No, those are different graphs.
Wouldn't matter because the data set size is essentially given, right? So you don't.
So what they do is that the first experiment they run is with a relatively small model, like 1.8 billion parameters. They train that model contaminated. They have, I think, only 1,000 contaminated examples, and then they test that those can be detected. That's how they show the power of the test, right? I don't know if you can show it theoretically.
But is the say if the test were not to work, right? So if whatever is being trained would still be invariant under permutation, that I think, as we discussed, wouldn't necessarily mean that it is not contaminated, right? So it's like a sort of one-sided kind of result.
Yeah, well, that's how statistical tests would work in general, no? Because you can either reject or not reject the null hypothesis. But if you don't reject it, it doesn't necessarily mean that.
True, but I mean, if the test is not, you wouldn't show non-contamination if the test was, if the null hypothesis was not violated, right? Just because by the very nature, right? It's a very specific property that's being tested here.
Yes, which is why they trained this model to show that it can detect.
Yeah,
but you're right. There is no. We don't know. It's also that they do speak about limitations. They mentioned this at the end, but also there is this point that what if it's the data set, training data is contaminated by the same data that was used to create the benchmarks? Then it won't work, right? So it's a very it does depend on assumptions, and it won't always work.
Yeah.
There is work to do here. I agree with that.
Right. Thank you.
Yeah. Okay. So the models they train, as I said, they train one model, GPT-2 model, 1.4 billion parameters, kind of small model, just to show that the test can work. And contaminated with a bunch of benchmarks, quite a few of them. There is a table down there. To test our ability to detect benchmarks at various duplication rates, we duplicate each of the data sets a different number of times, ranging from 1 to 100. Okay, so some of the So some of the benchmarks are used only once, others many times. There is a table here that will show the results. So you can see that they, I guess, kind of randomly contaminated. Some of the benchmarks are used only once. So this bull queue is the data set we used from the original example we showed. This MMLU is a collection of benchmarks. It's it's called massively large something. It's a collection of different data sets, right? And then some of these are from Wikipedia and a few other sources. So basically, you can see that when you have only one duplication, the test doesn't detect it. So these p-values are large, right? Either test doesn't detect it. However, when we get up to 10 duplications, the test starts working. Except that if you look at the simpler permutation-based method, the p-value never gets too small. You know why it can't get too small, but it still is indicative. But when we look at the sharded p-values, they get 0, basically. These are zeros. Yeah? Which is a good thing. With only 10 examples, we can detect contamination. Any questions? Cool. They do a few more experiments here. As the duplication count increases, the log probabilities. So this is a log of the p-value, right? Which means this horizontal line is 0.05, which is the usual threshold. The lower, because these are negative values, lower means lower p, right? So basically, we can see that even with 4 contamination examples, test can be useful, can detect those. 7 already works. 1, 2, not really. Sometimes it works with 2. This gray example here is, I think it's one example that can work, but the mean is not low enough. Okay, so we need to at least 4 examples for the test to work consistently. Okay. They also created a leaderboard, which they will maintain with new models. So this was published for ICLR this year, which means Llama 3, GPT-4o, and so on are not here. But maybe they added now. I haven't checked, but they may have added those. Now, sharding and permutation counts, right? Like what? Because with the sharding approach, we need to choose parameters. How many permutations? How many shards? I did an experiment here that shows that you don't want more than 20 shards because there is no improvement here, but it also can get worse, right? So between 10 and 20 is good. I think they use 10 or 20 shards, not too many, because they say if you have too many, there aren't enough samples left in each shard for the test to work reliably, right? You don't want to split them into two small pieces. On the other hand, if you have too many permutations, there is a diminishing returns. So again, there is no need to do too many permutations, like 25 is enough. Oh, also, of course, if you have too few shards, then the t-test won't work because the t-test is over the number of shards. If you have only 2 or 3, t-test won't work because it's also an asymptotic test. Okay? So you do need some shards and you need some permutations, but not too many of either. Other comments?
So the reason why you need each shard is viewed as like a data point from the same random variable, like a sample from the same random variable. So if you only have a few of them, you won't be able to calculate its mean effectively. Is that the idea?
Mhm.
Why you need? Okay.
I
wonder why. Sorry.
So you mean the number of shards?
Yeah.
So the t-test at the end works on the average of S, right, which is based on the shard. So if you have only 2 or 3, the t-test won't be powerful enough because it works the theory, the guarantees are also asymptotic there, which means you need at least some, in this case, 10 samples.
Yeah, that makes sense. And then I wonder why there's that like bump of worse performance at 20 and then it gets better at 50 and
Yeah,
then goes up again.
It kind of starts bouncing, right? I don't know. I guess it just, I don't know, just can't improve anymore. I guess if you have, yeah, I don't know why. This is a bit weird, but maybe we shouldn't look too much into it. The point is 10 is good enough. Just stick with that. But they do mention that with 20, it starts getting worse, and they justify that with too many shards, you might start missing. Oh, I know why. Because if you have, this can happen because of the shufflings, right? As you shard, sometimes you may not have enough samples. Other times you may have some, and then there might be a bit of uncertainty. Right.
One question that came to mind. So this p-value, right? It should be a property of the number of samples in that data set that are duplicated, right?
Yes.
So if would we expect the p-value to change with the model family? Probably, right?
Model family, or the training data, you mean?
Yeah. This p of theta, right? That is a model parameter that the model outputs. And as far as I can tell, this depends very strongly on the p-value at the end of the day does depend on, well, the model outputs and thus on the, I guess, on the model family as well. So
yeah, of course. So the p theta are the log probabilities that come from the model for this sequence.
Yeah, I just find it very weird to, well, this p-value wouldn't be any quote unquote objective probability, right? It's essentially is the difference in model sets I see consistent with the variance of the model outputs across the different charts. I don't know. Maybe I'm just thinking about it wrong.
Consistent with the variance.
Yeah, I mean this is what the test sort of is doing, right? It asks, is the fact that I see it in one ordering, I see a higher, predicted probability of that being a sample value versus just permutating it, right? And if I were to just naturally permutate, I probably would expect already some sort of variance, right? And the question is that difference in predictive probability within that natural fluctuation of permutative?
Maybe that's why you need more than one example in the training set to make sense.
What example? Sorry.
Maybe it doesn't make sense. Wait. Maybe so. If you have only, they are saying if you have only one repetition in the training set, you won't be able to detect it. No, it doesn't matter. No. Sorry, that doesn't matter. That's different. No.
Yeah, but I would expect that all of this must then depend on the model family itself, and
yeah, of course.
Yeah.
Well,
yeah,
they're detecting if the model it has been contaminated or not. The training they said. So of course it depends on the model, right? Or
yes.
am I...
Yeah. You. I think you're absolutely right. Of course, the connects with the model training and model.
Yeah, because the p-values you get from inference depend on the model, and then the test depends on those p-values.
Yeah.
Right.
So if I had a model, of course, that always outputs the same, no matter what, the test wouldn't work. But
then it's a useless model then.
Huh?
But then it's a useless model.
Yeah. Yeah, of course, of course. I'm
Right.
just thinking like as an extreme
Yeah.
case, how
Yeah.
this test actually is becoming useful. But yeah,
Mm.
because if you as we see right now, you sort of have to tune the parameters of the sharding and everything
Mm. Mm.
to get the maximum use out of it. But of course, you only know this after the fact when you already have contaminated a data set, so you can know that, right?
Mm-hmm. Mm-hmm. Yeah, exactly. Yeah. Yeah.
And I would expect those parameters, the optimal tuning parameters, depend on the model family, which you don't know beforehand, right? So
Oh, yeah, true. Okay, that's true. So basically, for the first experiment, the parameters they choose from experimentation because they know the model. They trained the model.
Yeah.
They can choose it meaningfully. They actually experiment here, right? And then they can choose because they know the ground truths here.
yes, exactly.
Exactly. Yeah, that's what you were saying. I see. Because they know the ground truths here, they can they can choose the parameters accordingly. But obviously, for other models, you kind of have to guess.
Yeah.
Because you don't know if it's good. Yeah, I get what you're saying now a bit. Yeah.
Yeah.
So so here we know the model, we trained the model, and we know how much how much the model was contaminated by each data set. This is our controlled experiment, just so we understand how the test works and what parameters to choose, right? But the next one is we are testing on models, both open and proprietary models. But for all of them, we don't know, we don't have access to the training data, actually. Like Llama 2, Mistral, this FIA, GPT-2, and a few others, right? Here, you can see the list of models here. So those are actually open models, but we don't have access to the weights. And now, if we run the test on a few benchmarks. I highlighted here a few suspects. First of all, Mistral looks very suspicious, right? I actually went to look at Mistral's performance tables, and it does do surprisingly well on this ArcEasy dataset. And then there is a clear indication of contamination.
Mhm.
It probably got contaminated with this one dataset, maybe by accident, right? Uh, there is also suspicion about Llama 2 and Mistral for this large benchmark, which is actually a collection of, it's a language understanding benchmark, but it's a collection of many other benchmarks. And then what they say is that here the numbers are low because for some of the questions here, the exchangeability assumption does not hold. Okay, and then they do follow-up experiment. They say GPT-2, the original one, was trained before this benchmark was made. Therefore, we look at the table and say, let me see, and then we say on some of the uh, um, here 14 of the tests that are in the MMLU benchmark, GPT-2 also shows as contaminated, but it can't be the case. And then they remove those benchmarks and then rerun on the remaining ones because they assume that the hypothesis doesn't hold there. Okay, and then they look at the p-values. There is a figure 4 here. Let me find that in the appendix. Go find it, and then they say there is no sign of contamination, but we can find the table here actually. 3, 4. Oh yeah, this is a large one. Then there is no. It was once a suspect, a little one. Where was it? Here. There is maybe math. The sphere may be contaminated with high school math mathematics, maybe. But mostly there is nothing uh, regular. Also, maybe this philosophy, but there are some, right? A few examples actually here, but not as it's not too bad. Like Mistral doesn't have clear contaminations. Oh, what is this? They were all contaminated with European history, right? So this is actually interesting to look into the examples. I didn't see this one before, but there is nothing uh, regular. There are a few examples we can pinpoint, but it's not terribly wrong. terribly wrong.
Do we know whether this the sort of performance on these tests is like something that generalizes across data sets? Say I have the same model class, parameter space, everything, and train it on 2 different data sets with the same size and say the same number of contaminated or duplicated issues. Would I expect the optimal tunings to be comparable, because then it almost makes sense to sort of calibrate this test on a standard benchmark?
Yeah, so they did change the parameters. I forgot to mention that. For the larger models, they did use more shards and more permutations per shard, right? They kind of linearly increased those, assuming with larger models, you might need more shards and more permutations. But probably you can just keep the same.
Or maybe or some sort of scaling behavior between the based on the data set size, right?
Yeah, I would like to see, isn't Grok fully open? Maybe if anyone can test it on Grok and then see what happens there, because that one is a massive model, and then that can help us with scaling behaviors, right? But not in this paper. I didn't see it here. I think it's a good starting point to develop these benchmarks, so we can keep track of all these models. I also became interested in this topic because GPT-4o suddenly started performing worse on specific data sets. People are speculating, is it worse, or was the previous one contaminated, or what happened, right? And then having tools to evaluate contamination, I think, is becoming more important because these models now consume everything.
Yeah.
Which means, can we? What does even generalization mean then? So these become important questions.
It's, I mean, of course, from a statistical perspective, if you test, 20 different data sets against for this, and you would expect 1 out of 20 to breach the 5% p-value just by chance, right? So
they did mention that they fixed some parameters to avoid p-value hacking. That's why in this experiment here, when they contaminate, they said we fixed this. We don't play with these numbers, like which benchmark is contaminated how many times, just so we don't end up with p-value hacking, right? Because if you do too many, sometimes the p-value will be low.
Yeah,
that's why they kept this fixed. But that's a very valid argument. If I guess we didn't play enough with these numbers to be worried, but maybe.
I mean, you can always, I think, adjust for the number of tests you're running, right?
Yeah. Any other comments? Cool. Next week we have the Khan paper that made a lot of noise on the internet. Damien is presenting, so come participate. Will be a fun paper. Thank you all.
Thank you.
Thank you, Vahan. Great paper.
Thanks, Vahan.
Thanks,
Bye.
Vahan.
Bye.